Bismillahirrahmanirrahim. Assalamu alaikum, dear students. This is our next problem. Problem having been chosen or selected or taken from the same book, Modern Physics by Paul A. Tipler. As usual, we first come to its statement. Okay, is a certain very bright star has an effective surface temperature of 20,000 Kelvin. Part A, assuming acceleration due to gravity g, sorry, no, assuming um, this g is a part of the spelling, assuming. Actually, dear students, this statement has been typed in math type software. Okay, so in math type software, the word assuming uh, appears in this sense that sometimes there is a mistake that perhaps G is written separately with assuming. Okay, no, this is not the case. Okay, a certain very bright star has an effective surface temperature of 20,000 Kelvin. Part A. Assuming that it radiates as a black body, what is the wavelength at which lambda mu lambda is maximum? In what part of the electromagnetic spectrum does the maximum lie? Okay, two parts. Second part, we have to decide with reference to the electromagnetic spectrum, which has various colors like violet, indigo, green, blue, etc. Okay, so we have to decide that range about the region of electromagnetic spectrum where that falls. Okay, now dear students, we are going to solve this problem, but before starting its solution in a proper manner, we will have to go through a few snapshots which will provide a foundation regarding the solution of this problem. So here, one, two, okay, only two snapshots are included in this part. Actually, dear students, snapshots are three, but two snapshots, that is to say, snapshot number two and snapshot number three are one and the same thing. Okay, they are alternate versions. The only difference is that snapshot number 2 and 3 have been taken from two different books. Okay, otherwise there is only two types of snapshots in this problem. Okay, so first we come towards the first snapshot. Okay, dear students, first snapshot deals with the Wayne displacement law for a black body. Okay, Wayne displacement law for a black body, lambda m capital T is equal to 2.90 into 10 raised to the power minus 3 meter Kelvin. Okay, where lambda m is the peak wavelength in spectral emittance curve. Okay, lambda m is peak or maximum wavelength. Okay, now add capital T is the absolute temperature of black body. Okay, hence lambda mt is equal to 2.90 into 10 raised to the power minus 3 meter Kelvin. 10 raised to the power minus 3 may also be termed as milli. Okay, so lambda mt is equal to 2.90 millimeter Kelvin. Okay, Now, dear students, second and third snapshot, which is usually, which should be assumed as a single snapshot, because these are just alternate versions of the same philosophy. Two snapshots have been taken or chosen or selected from two different books. Okay, this snapshot is about approximate correspondence between wavelengths of visible light and color. Okay, wavelength range, wavelength range in nanometer, and then color description. Okay, from 400 to 430 nanometer, color is violet. From 30 nanometer to 485 nanometer, color is blue. From 85 nanometer to 560 nanometer, color is green. From 560 nanometer to 590 nanometer, color is yellow. From 590 nanometer to 625 nanometer, color is orange. While from 625 nanometer to 700 nanometer, color is red. Okay, the same philosophy is described here in another book in a slightly different mode. Okay, wavelengths of visible light. Okay, 380 to 450 nanometer is violet, while from 450 nanometer to 495 nanometer, color is blue. From 495 nanometer to 570 nanometer, color is green, while from 570 nanometer to 590 nanometer, color is yellow, while from 590 nanometer to 620 nanometer, color is orange, while from 620 nanometer to 750 nanometer, color is red. Now we come towards part A in a regular formal manner. Okay, part A. According to Wien displacement law for a black body, lambda mt is equal to 2.90 into 10 raised to the power minus 3 meter Kelvin, where lambda m is the peak wavelength, T is temperature, K is Kelvin, m is meter. Okay, from here if we keep lambda m on one side, then temperature T will be divided after having been shifted to other side of equality, and it will become in the denominator. Okay, prior to shifting, it is multiplying with T, while after being shifted, T will become in the denominator. Okay, lambda m is equal to 2.90 into 10 raised to the power minus 3 meter Kelvin over T. This becomes equal to 2.90 into 10 raised to the power minus 3 meter Kelvin divided by 20,000 Kelvin. What we have done, we have simply put the value of T which is provided in the statement. Okay, this alternatively here, this implies that lambda m alternatively becomes equal to 1.45 into 10 raised to the power minus 3 into 10 raised to the power minus 4 meter. What we have done, actually, dear students, we have divided 2.9 by 2. So by dividing 2.9 by 2, it becomes half of this, that is 1.45 into 10 raised to the power minus 3 into 10 raised to the power minus 4. This 10 raised to the power minus 4 is which is with 4. Okay, with 2, that is, okay, we have 4 zeros with 2. So we have shifted these 4 zeros with 2 in the numerator. Okay, here it is 10 raised to the power plus 4, but after having been shifted to a numerator, it will become minus. Okay, so this alternative now lambda m alternatively becomes equal to 1.45 into 10 raised to the power minus 7. Okay, minus 4 and minus 3 will contribute as addition, and they will become 10 raised to the power minus 7 meter. Now we have reshaped 1.45 as 14.5. That is to say, we have shifted decimal one step ahead, and in doing so, as a result of this substitution or as a result of this rearrangement, our 10 raised to the power minus 7 will be changed to 10 raised to the power minus 8 meter. Next, once again, we have reshaped 14.5 as 145. That is to say, we have shifted decimal one further step ahead. Okay. So when 14.5 has been shifted to 145, then our 10 raised to the power minus 8 will be transformed, will be changed, will be shifted to 10 raised to the power minus 9. Okay, and we know that 10 raised to the power minus 9 is always nano. Okay, 10 raised to the power minus 9 is nano, while 10 raised to the power plus 9 is giga. 10 raised to the power minus 6 is micro, while 10 raised to the power plus 6 is million or mega. 10 raised to the power minus 3 is milli, while 10 raised to the power plus 3 is kilo. Okay, and hence our lambda m finally becomes equal to 145 nanometer, 145 nanometer, 145 nanometer. Now we come towards part B. Dear students, about part B, we have taken this study material, these wording. I have taken this from Wikipedia. Okay, anyhow, whether it has been chosen from Wikipedia or from some book, it is quite relevant to this problem, and on the basis of this we will solve part B. Okay, so as a helping tool to part B, we have added this portion, these wording. Okay, ultraviolet, that is UV light, is a type of electromagnetic radiation. Ultraviolet light has a shorter wavelength than visible light. In physics, ultraviolet radiation is traditionally divided into four regions. Okay, which four regions? We come towards those four regions. First region is near. Near region is from 400 to 300 nanometer. Then middle region is from 300 to 200 nanometer, while far region is from 200 to 100 nanometer, and extreme region is below 100 nanometer. Hence, lambda m falls under ultraviolet region within the electromagnetic radiation. Okay. Hence, delta m falls under ultraviolet region within the electromagnetic spectrum. One 45 nanometer, 145 nanometer, 145 nanometer, 145 nanometer. This is okay, dear students. Violet starts from 380. From 380 to 750 nanometer colors are given, and shorter than these is ultraviolet. Similarly, from its equivalent snapshot, from 400 to 700. Okay, from 400 to 430 color is violet, while below 400 that is ultraviolet. Okay, so in presence of these ongoing material, we have decided that our lambda m, which is 145 nanometer, lambda m which is 145 nanometer, falls under ultraviolet region within the electromagnetic spectrum. And this is the end of our problem. This is the end of our video. Till next video, Allah Hafiz.